I'm going to simulate a little bit what our brute force approach does and see what are the values of the number of products function for different values of t, right? So let's see, when the amount is 1, when t equals 1, what is number of products of 1? How many products could be there packed in total with total time 1? Well, this one, 0 plus 0 plus 1 divided by 1, 1, plus 1 divided by 2, which is 0. So we have only one product, right? Then, let's see how many products could there be packed for t equals 2. 1 plus 0 plus 2 plus 1. So that is a total of 4, if I'm correct. Nice. Now, let's see for t equals 3. 1 plus 1, 2 plus 3, 5 plus 1, 6, right? So 6 total products. Let's see for t equals 4 also. 2 plus 1, 3 plus 4, 7 plus 2, 9. All right. Let's see for t equals 5. 2 plus 1, 3 plus 5, 8 plus 2, 10. Awesome. And let's take one more t, for example, t equals 6. 3 plus 2, 5 plus 6, 11 plus 3, 14, right? And of course, so on and so forth. I'm not going to write all the values, but let's just see what happened here for the first 6 values of t. As you might notice, which is a thing that we've also talked about, the number of products function only keeps increasing. And this is obvious, right? I mean, it's obvious that our workers will pack more products in 5 units of time than in 2 or 3, right? So as long as the amount of time gets increased, the number of products will also get increased. So one observation here is that the number of products function is increasing. And this is all we need to know. If this function is increasing, can you figure out how we can use the binary search approach to find out what is the minimum needed time? Well, first of all, for this example, the minimum number of time is 4, right? So the answer is 4. And why is that? Because if we take a look at the values, 1 is not enough, 4 not enough, 6 not enough, 9 packages. This is the first number of products, which is greater than or equal to k. So, if we have imagined number of products being an array instead of a function, we have an increasing array, and we need to find the first value which is greater than or equal to a specific value. That, of course, could be done with linear search, as we do in the brute force approach, but also with binary search. Let's see how on this example. For example, if I would apply binary search here, as I've said, just imagine, we won't make an actual array out of number of products values, but just imagine it was an array, right? Again, I'm taking only the 6 values. It holds true for 100, 1000 values, doesn't matter, right? If this was an array, how would I apply binary search on it? Well, I'm looking for a specific index, right? For a specific position. The first position, the first index, which has a value, the value at that specific index is greater than or equal to k, right? And here, obviously, the function is 1 indexed because t is always greater than or equal to 1. And as you can see, at t equals 4, at the position 4, we have our first value. So what I would do is exactly the way that I'm binary searching a value in an array. I'm going to start with my left and right pointers at the start and at the end of the array, right? Which means that I am looking for the first value greater than or equal to k in the whole range. Now, what do? I compute the middle, of course. 1 plus 6 divided by 2, which is 3. And I find the middle pointer here. what am I going to do? Exactly like in the arrays case, I'm going to look at the value on that position. So the value of the function with argument 3, number of products of 3, which is 6. And I'm going to compare this 6 to, of course, my 7. And what do I see? I see that this 6 is less than 7. Can you think of what's going to happen next with this in mind? So because this 6 is smaller than our actual value that we are looking for, our k, and also very important because the function or the array, how you want to look at it, is increasing, every value on its left will also be less than k, right? Because those values are less than the value on the middle position. So of course, if the value on the middle position is less than k, everyone is less than k. So we have already figured out that there is no need to look for that minimum time, for a minimum time which is less than or equal to this 3, right? So what we do here is that figure out that we don't need these values, we don't need to look here. So our searching range now will become this one. I'm going to move the left pointer on position middle plus 1. Because if there is, because the first value greater than or equal to k obviously could be only here, right? On the right side. So on my first iteration of the binary search, I've moved the left pointer to position mid plus 1. And as you can see, obviously, I end up with a searching range, which is of length of size half the original one, right? Now, let me erase this. On the second iteration, left is here, right remain there. The middle pointer is, of course, here. What I'm going to do again, compare the value for the middle argument, number of products of middle, which is 10, to our k. And what do I see? I see that this value is greater than k. What does it mean? First of all, this means that 5 is a valid amount of time. So if I gave the workers 5 units of time in total, they could have done the job. So I'm gonna remember that 5 is a possible answer, and this is very important. I say only possible answer because I'm not sure if it is the minimum one. I know that 5 is a valid amount of time, but I don't know yet if it is the minimum valid amount of time, which the problem asks for. So I will keep in mind that I found 5 as a valid amount of time, but I am also going to continue the search to look for a smaller one. Where would I look? Well, if I know that number of products of 5 is greater than or equal to k, right? And because the function is increasing, obviously I know that each and every values on its right are going to be also greater than or equal to k. So I know that each and every time, amount of time, right, which is greater than 5 will also be valid. So what do? I only remember the 5 because if I know that 5 is valid, 6 is valid, 7 is valid, of course, I don't care about 6 or 7. I need the 5, right? Because it's the smallest one. So I only remember 5. And if there were to be another solution, which is not 5, it would obviously be on its left. So a smaller one, right? So basically what I'm doing is that I mark 5 as my current best solution. This is the minimum amount of time that is valid that I have found so far, but I'm going to continue looking for smaller ones because there might be smaller ones. In order to do that, I'm going to move the right pointer to position middle minus 1 to only look on middle's left, right? So on our next iteration, we will have left equals right equals 4. Now, obviously, the middle is also on this position. I check the value on the middle, number of products of 4, which is 9. I compare it to k, and it is indeed greater than or equal to k. And what do I do now? I have just found another valid time, which is also less than my current best solution. So I'm going to update the solution to 4. Now 4 is the minimum amount of valid time I have found so far. But again, I won't stop because there might be some other values on its left. So what do? I set right to position middle -1. And now, on the next iteration, left is 4, right is 3, and obviously we won't do nothing because this is not a valid search range, right? Left became greater than right, so my binary search stops. And what's the solution that I found? I found 4, right? I found 5 first, and then I found 4, which is less, so I'm going to stick with 4. So what our binary search does is what it basically does on every other array, but with a small gimmick here, which is to also store a variable to have the current best answer so far. Let's see how the code looks for this. Actually, before seeing the code, let me illustrate you another more general case, just to make sure that you've understood. So let's say we have the number of products and we have all its values, right? I don't care about the values. I won't write the values, but let's say we have, I don't know, number of products of 1 is here, of 2, of 3, of 4, of 5, of 6, and you got the idea, 7, 8, 9, 10, right? Now, if let's say left was here and right was here, just to make sure that you've understood on a general case, the middle would have been first here, right? So, again, there are only 2 scenarios. The first scenario is the one in which number of products of this middle, so this value right here, is actually less than k. In this scenario, where this value is less than k, we know for sure that all of them from left to middle are less than k, because again, we have an increasing function, right? So in this scenario, where number of products of middle is less than k, we don't need to look anymore on the left because we won't find any solution, right? Those will be definitely useless operations that our brute force approach did. So on the next step, I'm just going to jump here and I will only look starting from the next iteration in this range, right? Make sense? Awesome. Now, in the second scenario, where let's say the value on the middle was actually greater than or equal to k, right? One thing that I know is that because the function is increasing, everything on its right is also greater than or equal to k, right? Awesome. So, what do I do? What do I know? I know that every time that is greater than or equal to 5, every amount of time is going to be valid. But obviously, I only care about the minimum one, right? So why would I don't know, remember 7 or 8 when I know the 5 is smaller and is also valid, right? So what do is that I mark the current answer. Let's say we'll have a variable answer to be 5. And because we know these are good, but greater, there's no point in searching here anymore. So what will I do? I am going to continue my algorithm because I might have some other solutions. Let's say maybe also on positions 3 and 4, I had values greater than or equal to k. So I need to continue my algorithm. 5 is not my final solution. But what will I do is that I won't even look here. I'm going to go directly to right equals mid -1 and continue the search from there, right? So this is how we do it. And of course, on the next iterations, we are going to eventually find also those true values, and we are going to stick with always the smallest one, right? Awesome. Now, let's see how the code looks like for this approach. All right, here is the algorithm. So as you can see, I am starting with my left endpoint at the smallest value that t can take, which is 1, and with the right endpoint at the greatest value that t can take, which is k crossed max time. Then I'm starting my binary search. So while the searching area is still valid, while it still makes sense, so left is less than or equal to right, I compute the middle amount of time, left plus right divided by 2. And then I check how many products are made in that middle amount of time. If the number of products is less than k, so obviously that's 2 less time, and also all the amounts of time less than it are not good, I am going to set left to be equal to mid plus 1. So at the next iteration of the while loop, I only look in the right half of the searching area. Else, if the number of products is greater than or equal to k, this means that I found a possible solution, which is also the smallest one I found so far, right? Because remember, once I find the solution, I always continue the search on the left half. So I continue the search in a searching area which consists of only smaller values. So each time I have found a solution, which is a valid amount of time, which is mid, I can directly assign mid to answer. I don't need to do something like answer equals middle, minimum, the minimum between answer and middle, because middle will always be less than the value of answer, right? So answer equals middle, and then I continue the search for maybe a better solution. So for maybe a smaller amount of time, which is why I do right equals mid minus 1. And then go again on that left or right half, do the same thing. And in the end, when the binary search finishes, I just return the answer. The other thing that you should notice is that the number of products function is the exact same that we have written for the brute force approach, right? So again, I'm not making an array consisting of all the values. That would have been a brute force approach, because if I want to make the array, I have to compute all the k crossed max time values, because I don't know obviously where the answer is. So I don't do that. I just keep the function and call it whenever I need it, right? So I call it for every middle amount of time that I need to check. And this is all. And I check a number of different amount of time, which is equal to log of the length of the searching area, right? So remember, when we searched for a specific value in a sorted array of n elements, that was big O of log of n, right? But here, our searching area is not of length n. So also be careful with this. It is of length k crossed max time, right? So I start off with the searching area of length k crossed max time, and then I either keep the left half or the right half of it, which is k crossed max time divided by 2. And then let's say I kept the left half. Then what do? I keep the left or the right half depending on what the algorithm does of this one. So let's say I keep this one, and so on and so forth, right? So I start off with a searching area of length k crossed max time, and at each step, the searching area basically has half the length of the previous one. So how many times can I divide k crossed max time by 2 until I eventually end up with a searching area which has basically 0 elements? That is log, right? We are performing in the while loop log of k crossed max time iterations. So let's write it here. Log of k crossed max time iterations. And for each iteration, what do we do inside the while loop? Well, let's see. Compute the middle, constant. If number of products of mid is less than k, compute the number of products of mid Remember the time complexity of the function? It was big O of n, right? Because it gone through each and every worker. So I do a big O of n here, and then all of those are constants, right? So for log of k cross max time times, I do a big O of n to compute the number of products. So the final time complexity of this algorithm is actually big O of log of k crossed max time, right, crossed n. And this is a good time complexity. I mean, it's obviously not big O of n or big O of n log n, but that's the beautiful part about the log function. Even for very large values, the log function still gives us a small number, right? So let's say a very large value could be 2 to the power 64. That's like, I don't know how many billions. I think it's something like 10 to the power 18, right? So imagine 19 zeros, that kind of number. When you apply the log function on it, you are still left with 64. So this is why binary search is so powerful. You can search for information or solutions for the problems in a very large searching area, but still the number of iterations done on the binary search until it ends is very small. So this k crossed max time could be something like, I don't know, the greatest value can take, let's say 100,000, for example, and the greatest value max time can take also 100,000. It's still log of something like 10 to the power 10, which is even less than 64. So big O of n crossed log of this, right? Don't remove this from the time complexity, because the constant, if it's even 30 or 60, it's a meaningful constant, right? And yeah, this is it. So this is a perfect example of how to start with a brute force approach, identify which stage of it, which part of it is the one that can be optimized, and use some learned technique or data structure to optimize that part, and you'll have your optimal solution. All right. As always, see you on the next one.